Welcome back, chemistry fans. Tonight we're going to try and finish up topic 3 in unit 2. And so we've got a little bit of a cleanup to take care of first, though. Unfortunately, we left off a few topics and we need to go back and finish those first before we move on. So one of the things we left off is, how do we know that the average atomic mass is true? How do we get this data? Well, there's a machine called a mass spectrometer, spectrometer. And this mass spectrometer, it's this device that sits on a counter. It's big, it's heavy, and it will heat up. And whenever it heats up, it then can emit a high beam of energy that, if you put a sample in front of, will cause it to turn into a gas. Well, then this gas, depending on how heavy it is, it will move further faster. So if you look in this image, the lighter isotopes will be attracted to one side of the detector, and the heavier isotopes will be attracted to a different side. And of course, this happens mostly because a magnetic is pulling this beam, causing it to bend, and that's what causes it to move towards the detectors. Well, what you get from that then is a graph that looks somewhat like this here, where it has multiple lines depending on how many particles, how many compounds are in the sample. Well, it not only tells you what the weight of those samples are, but it tells you what the percentage is in the sample. So if we were to know that 72 is the weight of pentane, it would tell us that the relative amount of it, it's less than some of the other compounds that are in this. And so we could calculate what its percentage is of the pentane, then we could solve the crime, probably something along those lines. Well, another use for it is for us to learn what the isotopes are inside of a sample of an element. And so when we take these samples, what we can look at is these numbers down below represent then the mass numbers. And so we would have two elements. They have the same number of protons. Their mass numbers are 10 and 11. And so then we can estimate what their percentages are, and we can figure out what the average atomic mass is through the same formula that we did before. We would take the percentage multiplied by the mass number of the samples. So if we were to do that on this next example here, what you would find is that I've got one sample, it weighs 90, and it's at about 50%. I have another sample at 91, and it looks like it's somewhere around 5%. I have a 92, and it looks like it's about 10%. And then same thing for 94. It looks to me like 94 is somewhere hovering around also maybe 10, maybe 12%, something close to that, 50, 60, 75. I'm off by a little bit here. So, oh, those are 20%. Doggone, that's me being an idiot. So I've got, instead of 5%, I've got those being 10% and 20%. That's what I have here. So I've got 20, 20. This one was about we'll call this one, maybe not 20, we'll call this one 15. We'll do that. And then the numbers will work out correctly. 15, 10. And then the final one would be the 96, which is way out there, and it's the 5%. If we take the time to multiply the weights times the percentage of each one of these, so it'd be 90 times 0.5, which is 45, 91 times 0.1, which is 9.1, 92 times 0.15, and that's 13.8, 94 times 0.2, 18.8, and 0.05 times 96, and we would get 0.05 times 96, we would get 4.8. Add all those together. 45 plus 9.1 plus 13.8 plus 18.8 plus 4.8, and what we get is 91.5 as the average atomic mass. Now take that into comparison with what the average atomic mass is for some element that weighs 91.5. We got to go find it on the periodic table. 91.5, it's probably going to be zirconium. It's somewhere close to that 91.2 amount. So it's probably because of my estimates. They're not very good. So that gets us pretty close to it. Okay, so that's how we work with these mass spectroscopy graphs. So here is the first one that we saw on the example. And with this, it's got just 2 isotopes. So this one's a much easier one to figure out. However, what I'm going to do, because this one looks like this one should be somewhere here around 75. Let's say that that one's at 75. Let's ignore all this up here. And this one down here is roughly 25. So we've got 10 times 0.25, and I've got, what is that? 11 times 0.75. If we add those two together after they've been multiplied, 10 times 0.25 and 11 times 0.75, we get 10.75. All right, so we go and find our element that weighs somewhere close to 10.75, and you would see that that's going to be boron, was that element sample. Now, reality is, you could have probably guessed that. What element's weight, you know the average has to be somewhere in between there. Well, you probably could have guessed. You could have guessed and said 10.5. You could have looked on the periodic table and found that out. So it doesn't have to be an exact science to get the estimate, but it does help for you to know how to go about doing that. Here's one more of them. If we were to guess, where does it look like the average is going to be? It's going to be somewhere around 72, but we need to figure this out. Now, this one does not have percentages. What it has is a relative amount. So we would have a total of 16. So we would have to do 9 divided by 16, 6 divided by 16, and 1 divided by 16 to figure out their percentages. So they, for whatever reason, did not give us the percentages. This is 0.56. This is 0.38. And this is 0.06. So we take those percentages, multiply them by the weights, 70, 72, and 74, and we will get the average atomic mass. So 70 times 0.56, that's 39.2. 0.38 times 72, that's 27.4, and 0.06 times 74 is 4.4. We add those together, 0.2. 27.4 plus 4.4, and you get 71. What element weighs 71? Well, let's go find out. What element is close to 71? And it's somewhere in here. Germanium, it looks like, is probably what the answer should have been, something like that. That's 72, close enough. Okay, so here we go. We're moving on now to calculating a molar mass. So we did average atomic mass. Now what we're going to do is we're going to work on something called molar mass. The molar mass is the weight of a molecule. It's how much that molecule weighs if I had a whole bunch of it. So you don't need to know what a mole is. We haven't yet discovered that piece of the puzzle, but you just need to know that we're adding up weights. That's all it is. Now, if we go to formula mass, it's a little bit different. We're not going to worry about that one this time. I want you to focus on molar mass, but formula mass works the same way. You just add them up. It's just when we apply them, it will be the same. Formula mass is whenever we want an empirical formula versus when we need just the molecular, the weight of the molecule by itself. So here we go. I've got 2 elements. I've got H and Cl. I go on the periodic table and I find out the weight of hydrogen is 1. I find out the weight of chlorine is 35.5. I add those together and I get 36. Well, what if the formula was not that simple? What if it had more elements? What if it's C6H12O6, glucose, C6H12O6? So there are 6 carbons. So it'd be the weight of carbon. Carbon weighs 12.01, we would multiply it by 6. There are 12 hydrogens, so it'd be 12 times 1.007, and the oxygens are 15.999, and there are 6 of those. So we would multiply all of those, add them together, and that's where we come up with our mass of 180. It is just that simple. So we are going to practice that right now. We're going to use, in conjunction, a periodic table to go and find out the masses of these molecules. Well, neon is not a molecule. It's just an atom, but we got to start somewhere. So let's practice that. Neon is right there. Its weight, let me blow this up so you can see it just a little bit better what those weights are. 20.18. So the mass of neon, 20.18. I think this is the end of the topic too. It's just that simple, yeah. So hydrogen, each hydrogen weighs 1.007, but there are 2 of them. So I will do 2 times 0.007, which will be 2.014. Now the units on these are grams per mole. Grams per mole. And you're like, well, what is a mole? Don't worry about that yet. We will talk about it, I promise. All right, so here we go. Calcium. Let's go and look up the weight of calcium. Calcium. It's over on the left side of the periodic table. Calcium weighs 40.078. 40.078. So let's do that. There's only 1 calcium. Okay. But there are 2 chlorines. So it would have to be 35.453 times 2. I went and looked up the weight of calcium, of chlorine, 35.453 times 2 plus 40.078. My total weight is 110.984. Let's do, well, I got 2 more to go. Aluminum. The weight of aluminum is 27.982. 27.982. The weight of 2 oxygens, 15.999. The weight of 2 oxygen, hydrogens. So I got to add all that together. 27.982 plus 2 times 15.999 plus 2 times 1.007. And what you get is 61.994. Okay. Well, here we go on the last one. The last one is probably the most difficult because it has this funky asterisk in the middle. Well, the asterisk in chemistry does not mean multiply. It simply means to add. So for whatever reason, they decided not to use a plus symbol. They're using an asterisk. So I'm going to have to go and look up what the weight of copper is first, Cu. Copper is 63.546, 63.546. 0.546. I've got 1 sulfur, it weighs 32.06. I've got 4 oxygens, each weighing 15.999. And then notice this 5 in front. That is called a coefficient. It means that there are 5 waters. It doesn't mean there's 5 H's, it means 5 waters. So that means there's a total of 10 hydrogens. 5 times 2 is 10. And it means that there is an additional 5 oxygens. You can't see that right there. All right. So now I'm going to sum all of that together to get my final answer. 63.546 plus 32.06 plus 15.999 times 4 plus 10 times 1.007 plus 15.999 times 5, and you get your final answer, 249.606. All right, this is everything I need you to know about how to calculate a molar mass. Thank you very much. I will talk with you again soon.